So yeah, will graphs or machine learning win? Which one will come out on top? So the challenge is whether we can predict good or bad individuals for credit. And the data set is from German professor Hans Hofmann, which includes about 20 features and then a rating for whether the result was good or bad. It's actually a set of 6 ratings that go into a matrix, and we just simplified it down to a single feature. So we have a nice clean output. And the inputs are, some are numerical, or some are continuous, and some are different the discrete classifications like sex or marital status, relationship status, whether they have a telephone registered is just a binary yes or no. And so first, a little context on machine learning. So what is machine learning? Not what is it in terms of computer science terms, but just practically speaking. Machine learning is the way it's usually talked about as a set of tools and techniques for finding patterns, predictions, and identifying classifications in large data sets. So with this, I'm using more of a business application definition. And also kind of define it as it's a way of programming computers without actually programming the algorithms explicitly, but programming the algorithms based on the data that you feed into it and train it with. But the problem with that is that machine learning often becomes a black box problem. So you have your model and you have some accuracy, but you don't know why it's predicting something. And so in those cases, you have to find ways of evaluating what the relationships are, going beyond just the machine learning model. So some of the ways that you can probe the model is by literally probing it, putting in random inputs and kind of coming up with patterns between the outputs, changing one variable at a time, or combinations of variables, principal component analysis, multidimensional reduction. You can also do a model reduction where you create a simpler model based on your model, a more complicated model. Usually it'll be a neural network that you reduce down to something like a decision tree or a linear regression, and then you can find patterns, at least locally, for what the relationships are. But it's not great. With machine learning, if you get a really good model, you don't necessarily know what the patterns are. And so some of the an example of when this happens is if you apply for a line of credit or a credit card in the US and you get denied, they're required under federal law to send you a letter with the reason for your denial. Well, it's actually a neural network that determines whether they're going to approve you or deny you. And so they do a model reduction and come up with a reason to explain why they denied you, and then usually comes in a standard form with a couple of checkboxes. So it's usually a model reduction from the neural network to a often a linear regression, and then they fill in the letter. But that's the problem with explaining it. But in other cases, you might have a model that really works. For example, if you want to determine whether something's a wolf or a husky, I know, raise of hands, the white dog. Who thinks that's a wolf? Who thinks that's a husky? I don't actually know. I got this off of Google when I typed in wolf or husky, so I'm not sure which that one is. The one on the right is a husky, though. But there's a team that put together a classifier for a wolf or a husky, and they got it to be pretty accurate. Like with this couple of examples, there's only one that's wrong. The one on the bottom left, bottom left, it predicts a wolf, but it's actually a husky. But if you look a little more closely, and when they analyzed the model, they realized that they weren't looking at the dog. What they actually built was a snow detector, because pictures of wolves tend to be around snow, and huskies tend to be around more developed areas. And so they were basically, they ended up building a model unintentionally that checks whether there's snow in the picture and then determines it's a wolf if it finds snow. But moving on to graph databases. So the graph database that we like to use is Grakn. Grakn is a distributed on the back end, so you can put it on a cluster, not just a single server. Hyper-Relational database. It can handle different types of relationships. We actually have a talk at 510 where we will go over some of the applications that we do on Grakn with multiple types of relationships handled simultaneously. And it's kind of built for knowledge-oriented systems. And so some of the basic nodes, really, I'm not really the best person to explain this well. This is going to be Heichel's part, so bear with me a little bit. But I kind of think of it as there's 4 different types of nodes with the way that the database is encoded. You have entities, like your typical entities, which you would usually classify as a node in a typical graph database. But then you also have relationships classified as nodes and roles and attributes. And so what you end up having is relationships between these nodes. For example, a entity plays a role. So a person can be a husband or a wife or a father or a child. An attribute, a person can have an age. Actually, I think there's an example of a couple of these later on. Yeah, so Socrates or Plato, they teach, and an attribute of them is that they are mortal. Sorry, I'm glossing over this a little bit, but basically, this is an example of what the query language looks like when you define a human as a subset of a mortal, or has an attribute that mortal is true. But anyways, the point I'm trying to make with all this is that you can encode much more complex relationships in Grakn than you can in typical graph databases, and so it gives us a lot more flexibility for some of the analysis that we end up doing. But coming back to machine learning, because I mean my side of the talk was the machine learning, so I'm trying to make the argument that that's the better model. Basically, you have a bunch of data. The data set's about 20-some features, 1,000 data points, so it's not a huge data set. It's just a kind of a example data set. It's also from 1994, so it's kind of old, but it's a complete data set, so it's been used for a couple of other examples at different talks and papers. But the good or bad attribute, whether the credit ends up being a good credit line or a bad one, was a couple of different attributes that made up a matrix. We basically just used a single good or bad tag in that. And then we converted the categorical variables into dummy variables so we can shove them into a machine learning model. Because except for AWS machine learning, which we'll show you in a little bit, you kind of have to work with numbers. You can't put in like sex, male or female, into a machine learning model. You have to give it numbers so it can work with that. And then, of course, you have model selection based on the type of data and what you're trying to do with it. And then optimizing the model, which we did a little bit of, but didn't go too far in that. So typical machine learning, load the data, check it, split it into test and training data. We had about a 70-30 split in the true being good credit and false being bad credit. Oh. There we go. So about a 70-30 split. With the randomization, we had about a 70-30 split too. Converted all the features that were not integers. Integers we could leave as integers. Everything else we converted into dummy variables, and then converted the results of the matrix, the good and bad, into ones and zeros, and there's a list of our features that we shove into the models. So skipping down to the results, because you guys are probably tired of staring at code by now. With naive Bayes, with two different ones, Bernoulli and Gaussian, which typically you'd want a Bernoulli naive Bayes for binary data, even if only some of your data is binary, but we didn't really do any optimization. We were just kind of trying to see what we'd get out of it. We got about, was that overall is 75 for Bernoulli and about the same for the Gaussian one. Except that one was a little bit better balanced. In most of these models, it ends up being the case that the model is inaccurate on the negative cases because there's less of them. So it ends up being overfitted or fitted better to the positive cases, which is another topic with this whole topic of machine learning versus graphs that I'll touch on a little bit later. But those are kind of the results that we got. But then if you want to see whether what's actually causing these relationships, so like the decision tree, decision tree is about 70% accuracy, but you know, just for argument's sake, if we want to see what actually goes into that, this is what the tree looks like. So if we take a closer look, we can actually see and analyze the decision tree that gets created based on the training data. And so it's not the case with decision trees that the higher level nodes are more important. Kind of hard to see here, but it's actually the case where after a split, if they're more balanced, that's a more influential node. Whereas if they're less balanced, so like you get 2 on one side and 48 on the other, there's not a lot of information gain, so that's not an influential node. So when you're trying to describe how does this model work, you'd look at the nodes, the splits, that have a pretty large number and a pretty even split of basically that have a high information gain, and then use those to describe some of the decisions that go into the model. But it's also pretty complicated. Like trying to explain to someone you got rated as having bad credit because you, let's see, the first thing is the duration of your credit, followed by your credit amount, and then a couple other things. You can't really put that into a letter, at least not a very short letter. But that's kind of the best you can do with decision trees, where you can actually get into the tree. If you're working with neural networks, you can't even get into the network to see how it works. Oh, right. And so moving on to the machine learning, AWS machine learning, it's a microservice that AWS offers. What we did is we basically took the same data set with the same randomization that we used for our models that we ran on just sklearn, and we exported the same randomized data and plugged it into AWS machine learning to see, you know, how would a neural network perform. And so the results that we got, I don't know how well you can see that, but basically we got pretty comparable results. In a couple of different models that I tried, got between 80 and 84%, so better than Naive Bayes better than decision trees. Not too much better, a little bit, but I couldn't tell you what's going into this model. I have no idea what's causing it to make one decision or another. It's just kind of a overall result for the accuracy or the F1 score. And it's also biased pretty heavily towards predicting correct results accurately. So that's one of the big limitations of machine learning. You can see why the previous speaker was switching laptops. But yeah, the cool thing with AWS machine learning is you can make an endpoint once you train your model. So in this case, I picked out a random data point that wasn't used to train the model, but it was used in the evaluation for later. And it gives you a result for the rating, along with the confidence for true versus false. So if you want to tune your model, in this case, for example, if you want to be more cautious because you don't want to give out $40,000 lines of credit to people you're not really sure about, you can tune it so you only approve the person if it's a 90% confidence in the positive. So 90-10% split. So if it's like 50-50 or 45-50, you kind of set a higher bar. But moving on to the graph database approach and seeing how that compares. So again, with the data set, German credit data, 20 attributes. Some of the ones which, with the graph analysis, graph database-based analysis ended up coming up as important are whether they were a foreign worker or a domestic worker, whether they had a telephone registered to their name, and whether they were renting a house, renting as opposed to owning, or I think other was one of the categories, but basically whether they were a renter, and then also the purpose of the credit and the amount. And so with graph databases, you can basically do rule mining where you don't necessarily have all of the data set available to you, basically with the open world assumption, where you might not have every case represented. For example, if you have a definition of what a dog is, you have a definition of what a small animal is, but you don't have a definition of a cat, assuming dogs and cats are similar. You could, with enough rules, you can deduce what another data point is that's not in your database. With machine learning, if it's not in the database, it doesn't exist. It'll never classify it as something it's never seen before. But with graph theory, you can deduce things that are not necessarily there. In some cases, that can be a bad thing because you might want to put more constraints on your model and your data. But in this case, what the guys at Grakn did is they put together horn clauses, basically assertions with different conditions, and then we're able to come up with a couple of rules of what led to a positive or a negative rating, or good credit or bad credit rating. And of course, putting all of that into Grakn queries, which is the query language for this database. Oh, and they also only looked at triple assertions, so would only look at a combination of 3 of the 20 features at a time. So obviously, if you have 20 features, you can have my math just went out of my head, but you can have a lot of different combinations, like 20 factorial different permutations of combinations that you can come up with. But in this case, they only looked at 3 at a time max. And the results were comparable to machine learning. Like, the machine learning wasn't great. It was only 1,000 data points, so that's not a great machine learning example. Typically, you want at least a few thousand, 10,000. Basically, if you take the number of features divided by the number of data points you have. Like here we only have a factor of 50, which is okay. I mean, we get some results out of it. It's better than just random guessing, but to get some really good machine learning, you really need, I know, probably a couple tens of thousands, ideally 100,000 data points. So with the rule mining, with Grakn and graph databases, it got similar performance to both AWS machine learning and naive Bayes. And then with naive Bayes, with the machine learning approach, we got about, let's say 70%, give or take, 75%. And on AWS, kind of hard to see there, but basically about 80%. And one model managed to go up to 84%, but it was with a different randomization. So with such a small data set, how it's randomized can affect the model. But then looking at, with the machine learning, like I said, I can't really tell you what's causing one model to make it one decision or another. Other than the decision tree, or if I was to do a model reduction, I have no idea whether it's the fact that they have a telephone on file or whether it's the amount of the loan that's making that decision. With graph theory, with doing rule learning, they were able to identify that some of the things that tended to cause a positive or negative were whether the purpose of the application was for radio or TV. So somebody that was applying for a loan or a line of credit related to a radio or TV service was more likely to have a good line of credit. And on the other side, somebody that was a foreign worker was more likely to have a bad line of credit. And here's some of the probabilities. Like with the first one, about 80% of the time that held true. With the negative example, bad line of credit example is about 67% of the time. So comparable to what we got out of machine learning. Not quite as good, but close. So kind of in summary, you get a little bit better performance with machine learning, but you're blind to what you're doing. With graph databases and rule mining, you can do a better job explaining what goes into different decisions, but it comes at the cost of complexity. So the number of compute cycles you would spend to do this on a 1 million row or 30 million row data set would be huge. Fortunately, if depending on which database you use, you can distribute the back end, so speed that up a bit, but still a lot more than if you were to do a machine learning model on 30 million rows. And also the complexity of looking at different combinations of rules increases exponentially with the number of rules. In machine learning, it doesn't. However, most machine learning models tend to treat the different features as somewhat independent of each other. So, in summary, transparent models, the ones that are easier to look into, like linear regressions or decision trees, are easier to train, or they're harder to train with large data sets. So they work well with small data sets. When you get to larger data sets, they're harder to work with. Less complicated models, but they don't represent as much of the information gain in the data. With the real goal would be to combine graph theory and machine learning. Another big difference between the two is that machine learning likes relational data. There's no good machine learning model for network type data, whereas graphs, everybody here knows, otherwise you wouldn't be at this conference, knows that graphs are what you go to if you have any kind of relationship data. And so what do we do with all this? The goal with what we're working on is to integrate machine learning with graph databases. So not just to have to choose between one or the other, but to have a solution where you can have machine learning on graph data. So you don't have to force the data into some kind of traditional square table, relational database management system type format, but that you can keep it as graph data and still have some machine learning algorithms that you can use on that. And so Berkeley Data Science Group and Grakn AI has a partnership to develop some of these things and optimize some of the algorithms. So stay tuned to both of us for some results on this. It's kind of an ongoing project, so we don't have any immediate plans for any releases, though we are going to talk about some of the products that we've developed at 510 at talk a little later on today. And there's the websites for both of our companies. And some of the applications that we want to target with this is we want to be able to characterize different topologies. So on the next slide here, these two networks clearly have different topologies. When you look at them, you can just tell. But how do you quantify that? How do you have a computer be able to tell that these are different? Another thing is to predict missing edges. So when you have a network graph and you don't know whether some edges are missing or you want to recommend some connections, we're working on ways of being able to make those predictions and then also give them scores for whether that's a likely connection that should be there or could be there, or if it's a weak one. And so one of the applications for that is as a recommender system. One of the things we're working on, if you simplify the graph, it reduces down to your traditional recommender system that you find on Amazon 10 years ago, not the stuff they're doing now, but Amazon 10 years ago, or Facebook friend recommendations. But it's capable, it can reduce down to that, but it's also capable of handling much more complex relationships that are more context dependent. And some of the other things is identifying outliers. So like in the previous talk, they were talking about identifying money laundering within graph networks. So we've also been working on some algorithms for classifying outlier nodes. And that kind of ties into the being able to tell the difference between topologies. If the topology around a node is different than what's typical for the world or the community that you're looking at, then that would stand out as an outlier and worth taking a closer look at. And then also classifying connection strengths, because the world isn't just nodes and edges. Those edges have different strengths, different types. There's a lot of different dimensions that you can put in there. And so that's some of the stuff that we're working on now. And yeah, for predicting connections, like the top and the bottom right both have 2 mutual connections. The bottom left has 5. But in which graph are you more likely to suggest that red and blue are connected? Where they know 5 random people, maybe people they both met at Starbucks because they go there at the same time, or the one with less mutual connections, like the one on the top, where maybe that's people they work with, and so they work in the same department or departments next to each other but never met, but are probably likely to know each other or to meet in the future. And if you'd like to see some examples, come see us in room 407 at 510. Gunnar and I will be presenting then. And we'll have some more examples of, in that case, we'll be showing you how to write a resume in a way that you can get past the search filter. So instead of, how often do you get an interview from submitting a resume online? Not very often, like 1% of the time, 5% of the time, depending on which study you look at. We used some of the stuff that I've been talking about to build a system that helps you figure out what keywords to put in there so you can make it past those filters. So 510, room 407. And thank you. If you want to get in touch with me, there's my email and Heikel's email. He's out sick. He probably would have done a better job explaining the graph stuff than I would, but feel free to reach out if you have any questions.